Rates of reaction and equilibrium. Objective, Section 1. Describe how to express the rate of chemical reaction. Describe 4 factors that influence the rate of a chemical reaction. Rates of a chemical reaction is essentially reaction kinetics. Key concepts. How is the rate of a chemical reaction expressed, and what 4 factors influence the rate of a chemical reaction? Here is some vocabulary: rate, collision theory, activation energy, activated complex, transition state, and inhibitor. This is heater plus meals. It's a chemical reaction that heats the food. Metal objects can be damaged by corrosion, but this process can be useful to hungry soldiers, truck drivers, and others who want a hot meal but do not have a place to cook it. Products now on the market use the heat given off by the corrosion reaction of an iron-magnesium alloy with salt water to produce a hot meal. Normally, the reaction takes place at such a slow rate that the heat released from the process cannot be used. But when the rate is increased by the addition of salt water, heat is produced rapidly. In this section, you will learn some ways in which the rate of reaction can be increased. Connection to your world. Let's discuss and relate. We'll use visuals, the instant meals, explain that all chemical reactions occur at rates specific to the nature of the reactants, and let's do some questions. How can the rate of the corrosion of iron-magnesium alloy be increased? Well, it's said right in the text that you're adding salt water, and that's exactly what's happening, by the addition of salt water. Name some situations where salt affects the rate of corrosion of metals. Possible answers: autos, salted roads in winter, metals on boats and houses near the ocean. Here is a picture. We're looking at rates. Rate equals distance over time. Speed is measured as a change in distance in a given interval of time. A world-class sprinter might cover 100 meters in 11.5 seconds. The speed, or rate, is 100 meters over 11.5 seconds, which will equal 8.70 meters per second. Collision theory. When you strike a match, it erupts into flame almost instantly and burns quickly. Some other reactions occur more slowly. For example, millions of years were required for dead plants beneath Earth's surface to be converted to coal. These examples show that the speed of chemical reactions can vary from instantaneous to extremely slow. The concept of speed is already familiar to you. The winning sprinter in figure 18.1 covers 100 meters in 11.5 seconds. She runs at a speed of 8.70 meters per second. Another sprinter takes 15 seconds to cover the same distance. She runs at a speed of 6.67 meters per second. Both 8.70 meters per second and 6.67 meters per second express rates of travel. Collision theory. Discuss and relate. Discuss. Tell students that the time required for a chemical change to take place may be less than 10 to the negative 6 seconds or greater than 10 to the 6 years. Draw 3 vertical columns on the board and label them very fast, moderate, and very slow. Ask students to suggest chemical changes that fit into each category. If they have trouble thinking of reactions that fit in the moderate category, suggest reactions that take place over several hours or days, such as food spoilage or the rusting of iron. We will do this on the board in class. Remind me. Figure 18.2, change occurs at different rates. Interpreting. Photographs list the changes shown above in order of speed from slowest to fastest. So from left to right, we have aging, ripening, and burning. Explain that the rates of chemical reactions are often measured by the decrease in the concentration of one of the reactants or the increase in the concentration of one of the products. Ask, what happens to the reaction rates? It slows down. Students may think that particles always react when they collide. Stress that particles form bonds when they collide, only if the particles have sufficient kinetic energy. In any given reaction, only a certain fraction of the particles have enough energy to react upon collision. As time passes, the amount of reactant, the red squares, decreases and the amount of product, blue spheres, increases. Rates of chemical reactions are often measured as a change in the number of moles during an interval time. Interpreting diagrams. Assuming equal time intervals between the boxes, how can you tell that the rate of conversion of reactant to product is not constant throughout this reaction? The number of additional blue balls products decreases in each successive time interval. If colliding particles have enough kinetic energy and collide at the right orientation, they can react to form a new product. A, an effective collision of reactant molecules produces product molecules. B, an ineffective collision of reactant molecules produces no reaction, and the reactants bounce apart unchanged. A rate is a measure of the speed of any change that occurs within an interval of time. The interval of time may range from fractions of a second to centuries. Figure 18.2 shows some familiar examples of rates of change. If 1/2 of a 1 molar piece of iron turns to rust in 1 year, the rate at which iron rusts must be expressed as 0.5 moles per year. In chemistry, the rate of chemical change, or the reaction rate, is usually expressed as the amount of reactant changing per unit time. The progress of a typical reaction is illustrated in Figure 18.3. Rates of chemical reactions are related to the properties of atoms, ions, and molecules through a model called collision theory. According to collision theory, atoms, ions, and molecules can react to form products when they collide with one another, provided that the colliding particles have enough kinetic energy. Particles lacking the necessary kinetic energy to react bounce apart unchanged when they collide. Figure 18.4 is a model for the reaction of hydrogen and oxygen molecules to form water. You can use 2 balls of soft modeling clay to illustrate collision theory. If you throw the balls of clay together gently, they don't stick to one another. This is analogous to colliding particles of low energy that fail to react. The same balls of clay thrown together with great force, however, stick tightly to each other. This is analogous to the collision of 2 high-energy particles that results in the formation of a product. You can also use modeling clay to illustrate another point about chemical reactions. If you roll clay into a rope and begin to shake one end more vigorously, you will come to a point where the clay rope will break. Similarly, if enough energy is applied to a molecule, the bonds holding the molecules together can break apart. Substances, when supplied with sufficient energy, decompose to simpler substances or reorganize themselves into new substances. This minimum energy that colliding particles must have in order to react is called the activation energy. In a sense, the activation energy for a chemical reaction is a barrier that reactants must cross to be converted to products. Figure 18.5, the activation energy barrier must be crossed before reactants are converted to products. In some of the slides to come, the questions will be answered that are part of the graph. Figure 18.5, explain that the diagram graphically depicts the energy changes that occur during a reaction. Point out that the activation energy barrier must be crossed before reactants can be converted to products. Explain that the activation energy determines how rapidly a reaction occurs at a given temperature. How does a large activation energy affect reaction time? It causes the reaction to be slow. Why? Well, think about it. A few molecules collide with enough energy to form an activated complex. You have an intermediate reaction that's part of the deal. Navigate. This is figure 5. Which are at a higher energy, the reactants or the products? The reactants are at a higher energy. Again, refer to the graph. Read. Is energy absorbed or released in progressing from the reactants to the activated complex? They are absorbed. Once the activated complex is formed, will it always proceed to form products? Explain. No, it could also revert to the reactants. Enrichment question. Inhibitors poison catalysts. How would adding an inhibitor affect both graphs? The activation energy would be higher than the graph for the reaction with a catalyst, but no higher than the activation energy without a catalyst. Here is another shot of the graph for your review that will be mentioned in the next slide. You can see in the energy diagram in figure 18.5 that when two reactant particles with the necessary activation energy collide, a new entity called the activated complex may form. An activated complex is an unstable arrangement of atoms that forms momentarily at the peak of the activation energy barrier. An activated complex forms only if the colliding particles have sufficient energy and if the atoms are oriented properly. The lifetime of an activated complex is typically about 10 to the negative 13 seconds. Its brief existence ends with the reformation of the reactants or with the formation of the products. The two outcomes are equally likely. Thus, the activated complex is sometimes called the transition state. Collision theory explains why some naturally occurring reactions are immeasurably slow at room temperature. Carbon and oxygen react when charcoal burns, but this reaction has a high activation energy. At room temperature, the collision of oxygen and carbon molecules are not energetic enough to break the oxygen-oxygen and carbon-carbon bonds. These bonds must be broken to form the activated complex. Thus, the reaction rate of carbon and oxygen at room temperature is essentially zero. What are two events that might occur after the formation of an activated complex? Products may form, or the activated complex may break up to form reactants again. Factors affecting reaction rates. Every chemical reaction proceeds at its own rates. Some reactions are naturally fast and some are naturally slow under the same conditions. However, by varying the conditions of the reaction, the rate of almost any reaction can be modified. The rate of a chemical reaction depends upon temperature, concentration, particle size, and the use of a catalyst. Collision theory helps explain why changing one or more of these factors may affect the rate of a chemical reaction. Temperature. Usually raising the temperature speeds up reactions, while lowering the temperature slows down reactions. At higher temperatures, the motions of reactant particles are faster and more chaotic than they are at lower temperatures. Increasing the temperature increases both the frequency of collisions and the number of particles that have enough kinetic energy to slip over the activation energy barrier to become products. An increase in temperature, therefore, causes products to form faster. A familiar example of the effect of temperature on reaction rate is the burning of charcoal. At room temperature, a bag of charcoal in contact with air does not burn. But when a starter flame touches the charcoal, atoms of the reactants, carbon and oxygen, collide with higher energy and greater frequency. Some collisions are at a high enough energy to form the product carbon dioxide. Factors affecting reaction rates. Discuss. Point out that an increase in temperature causes an increase in the average kinetic energy. The number of collisions increase because molecules are moving faster. More important, more collisions are effective. How do refrigerators prevent food from spoiling? Think about what we just said. The kinetic energy of reactant is reduced. Fewer particles possess sufficient energy to react. Everything slows down when you cool things down. The heat released by the reaction then supplies enough energy to get more carbon and oxygen over the activation energy barrier. When the starter flame is removed, the reaction continues. Concentration. In a crowded room where people are moving more rapidly, you may find yourself bumping into people more frequently than if you were one of a few occupants. Similarly, the number of particles in a given volume affects the rate at which reactions occur. Cramming more particles into a fixed volume increases the concentration of reactants and consequently the frequency of collisions. Increased collision frequency leads to a higher reaction rate. The rate of reaction depends upon the concentration of the reactants. A. In air, a lighted splint glows and soon goes out. B. When placed in pure oxygen, the splint bursts into flame, inferring what accounts for this difference in reactivity. Concentration of oxygen, reactant, is increased. The lighted splint in figure 18.6 only glows in air, which is 20% oxygen. It may soon be extinguished, but when the glowing splint is plunged into pure oxygen, it immediately bursts into flame. The increased concentration of oxygen greatly speeds up the combustion reaction. This is why flames are forbidden in areas where bottled oxygen is in use. Because a catalyst is not consumed during a reaction, it does not appear as a reactant or product in the chemical equation. Instead, the catalyst is often written above the yield arrow, as in the equation above. Northern lights. Generally, the spontaneity of a reaction is increased by heating the reactants. In certain reactions, however, other types of energy are more effective than heat. During periods of intense solar activity, for example, bombardment by charged particles causes a small fraction of nitrogen molecules in the upper atmosphere to dissociate, yielding excited nitrogen atoms. The green light of the aurora borealis results from the fluorescence of molecular nitrogen, which is produced when two excited nitrogen atoms recombine. Scientists who have heated samples of air in the laboratory have found that no amount of thermal energy is sufficient to reproduce the reaction that causes the green emission. Particle size. If you put a bundle of sticks on a campfire, they burn quickly. A log, however, burns more slowly. Small pieces of wood have more surface area than a log. And surface area plays an important role in determining the rate of reaction. The same is true for other chemical reactions. The total surface area of a solid or liquid reactant affects the reaction rates. The smaller the particle size, the larger is the surface area for a given mass of particles. An increase in surface area increases the amount of the reactant exposed for reaction, which further increases the collision frequency and the reaction rates. One way to increase the surface area of a solid reactant is to dissolve them. In a solution, particles are separated and more accessible to other reactants. Figure 18.7, an explosion destroyed this grain elevator. The minute size of reactant particles, grain dust, and a mixture of grain dust and oxygen in the air caused the reaction to be explosive. You can also increase the surface area of a solid by grinding it into a fine powder. Small dust-like particles, however, can be dangerous when suspended in air. As coal miners know, large chunks of coal pose little danger, but coal dust mixed with air is an explosive hazard because of its large surface area. The same is true of dust in a flour mill or a grain elevator, as the dramatic photograph in figure 18.7 shows. Catalysts. Increasing the temperature is not always the best way to increase the rate of reaction. A catalyst is often better. Recall that a catalyst is a substance that increases the rate of a reaction without being used up during the reaction. A catalyst increases the rate of a reaction by lowering the activation energy barrier. This is figure 18.8. Figure 8, visual strategy. We'll ask a few questions now. How does the catalyst affect the magnitude of the activation energy? That's question 1. Navigate. It lowers the activation energy. Question 2. Read. Does the catalyst change the amount of energy released in the reaction? No. Interpret. Along which of the two reaction paths are reactants converted more rapidly to products? The line for reaction with a catalyst. And here is another shot of figure 18.8, which is mentioned in the next slide. It is here for your review. Study it carefully. Catalysts permit reactions to proceed along a lower energy path, as figure 18H shows. Notice the activation energy barrier for the catalyzed reaction is lower than that of the uncatalyzed reaction. With a lower activation energy barrier, more reactants have the energy to form products within a given time. For instance, the rate of the combination reaction of hydrogen and oxygen at room temperature is negligible, but with a trace of finely divided platinum as a catalyst, the reaction is rapid. Catalysts are crucial for many life processes. Your body temperature is only 37 degrees Celsius and cannot be raised significantly without danger. Without catalysts, few reactions in the body would proceed fast enough. Enzymes are biological catalysts that increase the rates of biological reactions. When you eat a meal containing protein, enzymes in your digestive tract break down the protein molecules in a few hours. Without enzymes, the digestion of protein at 37 degrees Celsius would take many years. An inhibitor is a substance that interferes with the action of a catalyst. Some inhibitor molecules work by reacting with or poisoning the catalyst itself. Thus, the inhibitor reduces the amount of functional catalysts available. Reactions slow or even stop when a catalyst is poisoned. Section 2. Objectives: reversible reactions and equilibrium. Describe how the amounts of reactants and products change in a chemical system at equilibrium. Identify 3 stresses that can change the equilibrium position of a chemical system. Explain what the value of Keq indicates about the position of equilibrium. Next will be the key concepts. How do the amounts of reactants and products change in a chemical system at equilibrium? What 3 stresses can cause a change in equilibrium position of a chemical system? And what does the value of Keq indicate about the equilibrium position of a reaction? Keq, that's the equilibrium constant. Vocabulary: reversible reaction, chemical equilibrium, equilibrium position, Le Chatelier's principle, and equilibrium constant. Connecting to your world. For years, scientists tried to produce nitrogen compounds from fertilizers to increase the amount of available foodstuffs. Unfortunately, none of these efforts proved to be commercially successful. Finally, in the early 1900s, 2 German chemists, Fritz Haber and Karl Bosch, refined the process of making ammonia from elemental nitrogen and hydrogen. Their success came from controlling the temperature and pressure under which the 2 gases are reacted. In this section, you will learn how changing the reaction conditions can influence the yield of a chemical reaction. Connecting to your world. Discuss and relate. Ammonia. Use visuals. Point out that the 2 elements involved in the production of ammonia are gases, hydrogen and nitrogen, at room temperature. Do you think that controlling temperature and pressure of liquids or solids in a similar reaction would have had a similar effect? Why? Temperature might, but liquids and solids aren't sensitive to pressure difference the way gases are. Reversible reactions. From what you have already learned, you may have inferred that chemical reactions go completely from reactants to products, just as the chemical equation indicates. This is not usually the case. Some reactions are reversible. A reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactions occur simultaneously. One example of a reversible reaction is the following. The forward reaction, 2 moles of sulfur dioxide plus 1 mole of oxygen yields 2 moles of sulfur trioxide, and the reverse is also true. In the first reaction, which is read from left to right, sulfur dioxide and oxygen produce sulfur trioxide. Molecules of sulfur dioxide and oxygen react to give sulfur trioxide. Molecules of sulfur trioxide decompose to give sulfur dioxide and oxygen. At equilibrium, all 3 types of molecules are present in the mixture. Figure 18.9, discuss and relate. Reversible reactions. Explain that chemical reactions do not always go completely to products because they are often reversible. Once the products form, they may decompose to form the reactants. Does the reaction continue when the products and reactants are at equilibrium? Yes. How does a large activation energy affect reaction time? Reactants change into products, and products reform into reactants, but their net amounts stay the same. Equilibrium comes from the Latin word aequilibrium, A-E-Q, one word, meaning in balance. In a chemical system at equilibrium, the rate of the forward reaction is balanced by the rate of the reverse reaction. If the prefix dis means opposite or absence of, what does a state of disequilibrium indicate? Disequilibrium for a chemical reaction means the opposite of being in balance. Therefore, the amount of reactant and product is still changing. Here's another shot of figure 18.9. It will be mentioned in the following slide, and it is for your review. Study it carefully. In the second reaction, which is read from right to left, sulfur trioxide decomposes into oxygen and sulfur dioxide. The first reaction is called the forward reaction. The second is called the reverse reaction. The 2 equations can be combined into one using a double arrow. The double arrow tells you that this reaction is reversible. Figure 18.9 shows that this equation represents 2 opposite reactions. What actually happens when sulfur dioxide and oxygen gases are mixed in a sealed chamber? The 2 reactants begin to react to form sulfur trioxide at a particular rate. Because no sulfur trioxide is present at the beginning of the reaction, the initial rate of the reverse reaction is 0. As sulfur trioxide begins to form, however, the decomposition of sulfur trioxide begins. This reverse reaction proceeds slowly at first, but its rate increases as the concentration of sulfur trioxide increases. Simultaneously, the rate of the forward reaction decreases because sulfur dioxide and oxygen are being used up. Eventually, sulfur trioxide is decomposing to sulfur dioxide and oxygen as fast as sulfur dioxide and oxygen are forming sulfur trioxide. When the rates of the forward and reverse reaction are equal, the reaction has reached a state of balance called chemical equilibrium. Changes in concentration of the 3 components during the course of the reaction are shown in the graphs in figure 18.10. The graph on the left shows the progress of the reaction that starts with specific concentrations of sulfur dioxide and oxygen. but with 0 concentrations of sulfur trioxide. These graphs show how the concentrations of oxygen, sulfur dioxide, and sulfur trioxide vary with time. Left, initially sulfur dioxide and oxygen are present. Right, initially only sulfur trioxide is present. Question 1, navigate. Where on the graphs can you find the initial concentration of the reactants and products, the equilibrium concentrations? Initial concentrations are at the far left, and equilibrium concentrations are at the far right. Read. Which gas is most abundant at equilibrium? Sulfur trioxide is most abundant at equilibrium. Interpret how do the equilibrium concentrations of oxygen, sulfur dioxide, and sulfur trioxide compare? Enrichment question. Would these graphs change if you changed volume, pressure, or temperature? Explain. Yes, you can change the concentration of the gas by changing the volume of its container, pressure, and temperature. The graph on the right shows concentrations for a reaction that begins with an initial concentration of sulfur trioxide and 0 concentrations for sulfur dioxide and oxygen. Notice that after a certain time, all concentrations remain constant. At chemical equilibrium, no net change occurs in the actual amounts of the components of the system. The amount of sulfur trioxide in the equilibrium mixture is the maximum amount that can be produced by this reaction under the conditions of the reaction. The unchanging amounts of sulfur dioxide, oxygen, and sulfur trioxide in the reaction mixture at equilibrium might cause you to think that both reactions have stopped. This is not the case. If the rate at which shoppers move from the first floor to the second is equal to the rate at which shoppers move from the second floor to the first, then the number of shoppers on each floor remains constant. Applying concepts. Is it necessary that an equal number of shoppers be on each floor? Explain. No, the numbers can be different, but the number of shoppers moving between floors must be the same. Chemical equilibrium is a dynamic state. Both the forward and reverse reactions continue, but because their rates are equal, no net change occurs in their concentration. The escalators in figure 18.11 are like the double arrow in a dynamic equilibrium equation. The number of people using the up escalator must equal the number of people using the down escalator for the number of people on both floors to remain constant. Why is chemical equilibrium called a dynamic state? Because both the forward and reverse reactions continue. Although the rates of the forward and reverse reactions are equal at chemical equilibrium, the concentrations of the components on both sides of the chemical equation are not necessarily the same. In fact, they can be dramatically different. Figure 18.10 shows the equilibrium concentrations of sulfur dioxide, oxygen, and sulfur trioxide. The concentrations of sulfur trioxide is significantly greater than the concentrations of sulfur dioxide and oxygen. The relative concentrations of the reactants and products at equilibrium continue or constitute the equilibrium position of a reaction. The equilibrium position indicates whether the reactants or products are favored in a reversible reaction. Discuss reactants and products. Point out that in many cases the concept of reactants turning into products as described by a chemical equation is an oversimplification. Many reactions reach an equilibrium state in which the reaction mixture contains both reactant and product particles. The percent of reactants converted to products varies considerably. When hydrogen and oxygen combine to form water, for example, nearly all of the molecules react. In the reaction of hydrogen and nitrogen to form ammonia, the percent of reactants converted to product is much smaller. Stress that equilibrium refers to the rates of the forward or reverse reaction, not to the quantities of reactants and products. If A reacts to give B and the equilibrium mixture contains significantly more B, say 1% A and 99% B, then the formation of B is said to be favored. On the other hand, if the mixture contains 99% A and 1% B at equilibrium, then the formation of A is favored. Notice that the equilibrium arrows are not of equal length. The longer of the two arrows indicates the favored direction of a reaction. In principle, almost all reactions are reversible to some extent under the right conditions. In practice, one set of components is often so favored at equilibrium that the other set cannot be detected. If one set of components, reactants, is completely converted to new substances, products, you can say that the reaction has gone to completion, or is irreversible. When you mix chemicals expecting to get a reaction, but no product can be detected, you can say there is no reaction. Reversible reactions occupy a middle ground between the theoretical extremes of irreversibility and no reaction. A catalyst speeds up both the forward and the reverse reactions equally because the reverse reaction is exactly the opposite of the forward reaction. The catalyst lowers the activation energy of the reaction by the same amount in both the forward and reverse directions. Catalysts do not affect the amount of reactants and products present at equilibrium. They simply decrease the time it takes to establish equilibrium. What is chemical equilibrium? A situation in which the forward and reverse reactions occur at the same rates. Factors affecting equilibrium, Le Chatelier's principle. A delicate balance exists in a system at equilibrium. Changes of almost any kind can disrupt this balance. When the equilibrium of a system is disturbed, the system makes adjustments to restore equilibrium. However, the equilibrium position of the restored equilibrium is different from the original equilibrium position. That is, the amounts of products and reactants may have increased or decreased. Such a change is called a shift in the equilibrium position. The French chemist Henri Le Chatelier, 1850 to 1936, studied how the equilibrium position shifts as a result of changing conditions. Factors affecting equilibrium, Le Chatelier's principle, referred to the formation of banana oil, which was described on page 546. Write on the board the general word equation for the formation of an ester. Organic acid plus alcohol yields ester plus water. Add a reverse arrow to show the possibility of the opposite reaction. Remind students that the reaction was effective in the test tube to which anhydrous calcium sulfate had been added. Calcium sulfate reacted with water to form a hydrate, which limited the reverse reaction by removing a product. Write the equation for the dissociation of carbonic acid on the board. Carbonic acid yields carbon dioxide plus water. Explain that our bodies expel carbon dioxide to maintain the correct equilibrium between carbon dioxide and carbonic acid. During and after vigorous exercise, more carbon dioxide than usual needs to be removed to maintain equilibrium. What are some signs that the body is trying to reestablish equilibrium after exercising? A faster heartbeat and breathing rate. Also, there's bicarbonate involved in that reaction. He proposed what has come to be called Le Chatelier's principle. If a stress is applied to a system in dynamic equilibrium, the system changes in a way that relieves the stress. Stresses that upset the equilibrium of a chemical system include changes in the concentration of reactants or products, changes in the temperature, and changes in pressure. The following examples of applications of Le Chatelier's principle all involve reversible reactions. For simplicity and clarity, the components to the left of the reaction arrow will be considered the reactants, and the components to the right of the arrow will be considered to be products. Blue arrows indicate the shifts resulting from additions to or removals from the system. The arrows always point in the direction of the resulting shift in the equilibrium position, that is, toward the favored side. Concentration. Changing the amount or concentration of any reactant or product in a system at equilibrium disturbs the equilibrium. The system adjusts to minimize the effects of the change. Consider the decomposition of carbonic acid in aqueous solution to form the products carbon dioxide and water. The system has reached equilibrium. At equilibrium, the amount of carbonic acid is less than 1%. Adding more carbon dioxide disturbs the equilibrium. It increases the concentration of carbon dioxide in the mixture and causes the rate of the reverse reaction to increase. As more reactant carbonic acid is formed, the rate of the forward reaction also begins to increase. In time, the rates of the forward and reverse reaction again become equal, and a new equilibrium is established with a higher concentration of reactant carbonic acid. Adding a product to a reaction at equilibrium pushes a reversible reaction in the direction of the reactants. If, on the other hand, carbon dioxide is removed, the concentration of carbon dioxide decreases. This causes the rate of reverse reaction to decrease. As less reactant carbonic acid is being formed, the rate of the forward reaction is also begins to decrease. When the rates of the forward and reverse reactions again become equal, equilibrium is restored, but at a different equilibrium position. Removing a product always pushes a reversible reaction in the direction of the products. Farmers use this technique to increase the yield of eggs laid by hens. Hens lay eggs and then proceed to hatch them. If the eggs are removed after they are laid, removing the product, the hen will lay more eggs, increasing the yield. Similarly, as products are removed from a reaction mixture, the system continually changes to restore equilibrium by producing more products. I like this thing about the eggs. The rapid exhalation of carbon dioxide during and after vigorous exercise helps reestablish the correct CO2 carbonic acid equilibrium. This keeps the acid concentration in the blood within a safe range. Like I said, there's a bicarbonate factor here that's not being explained. But because the products are being removed, the reaction can never reestablish equilibrium. The reaction continues to produce products until the reactants are used up. Another example of this concept is found in the body. Blood contains dissolved carbonic acid in equilibrium with carbon dioxide and water. The body uses the removal of products to keep the concentration of carbonic acid within safe range. When the athletes in figure 18.12 exhale carbon dioxide, the equilibrium shifts towards carbon dioxide and water, thus reducing the amount of carbonic acid. The same principle applies to adding or removing reactants. When a reactant is added to a system at equilibrium, the reaction shifts in the direction of the formation of products. When a reactant is removed, the reaction shifts in the direction of formation of reactants. Checkpoint. According to Le Chatelier's principle, how does a system at equilibrium respond to a stress? It moves in the direction that relieves the stress. You remember, if I produce a precipitate, I'm going to push the reaction in the direction of the precipitate. What does that have to do with this? Carbon monoxide. Molecules such as carbon monoxide that are structurally similar to oxygen molecules can bind to the hemoglobin molecule. Therefore, they compete with oxygen for the same binding location. This competition is the cause of carbon monoxide poisoning because their affinity for the heme group is greater. Carbon monoxide molecules can displace oxygen molecules from hemoglobin. The equilibrium in this reaction lies far to the right because the affinity of the carbon monoxide for heme is approximately 150 times stronger than that of oxygen. So make sure you keep carbon monoxide out of your house and your car. Increasing the temperature causes the equilibrium position of a reaction to shift in the direction that absorbs heat. The heat absorption reduces the applied temperature stress. For example, consider the following exothermic reaction that occurs when sulfur trioxide is produced from the reaction of sulfur dioxide and oxygen. Heat can be considered to be a product, just like sulfur trioxide. Heating the reaction mixture at equilibrium pushes the equilibrium position to the left, which favors the reactants. As a result, the product yield decreases. Cooling or removing heat pulls the equilibrium to the right, and the product yield increases. Pressure. A change in the pressure on a system affects only gaseous equilibria that have an unequal number of moles of reactants and products. An example is the reaction you read about in Connecting to Your World. Hydrogen and nitrogen react to form ammonia. Imagine that the three gases are at equilibrium in a cylinder that has a piston attached to a plunger, similar to a bicycle pump, but with the hose sealed. A catalyst has been included to speed up the reaction. What happens to the pressure when you push the plunger down? The pressure on the gases momentarily increases because the number of molecules is contained in a smaller volume. The system immediately relieves some of the pressure increase by reducing the number of gas molecules. Figure 18.13. Pressure affects a mixture of nitrogen, hydrogen, and ammonia at equilibrium. A. The system is at equilibrium. B. Equilibrium is disturbed by an increase in pressure. C. A new equilibrium position is established for fewer gas molecules. Interpreting diagrams. What effect does a decrease in volume have on the number of gas molecules? Decreasing the volume shifts the equilibrium in the direction of fewer gas molecules. Figure 13, Visual Strategy. Study the diagrams and explain how equilibrium in A relates to equilibrium in C. Increasing the pressure on the system in A caused the reaction to shift to the right, producing more molecules of product in C. What kind of substance does a change in pressure affect? Gases. The industrial production of ammonia provides a practical application of Le Chatelier's principle. Write the equilibrium equation on the board. Based on the equilibrium equation, select ideal temperature and pressure conditions for the highest possible yield of ammonia. High pressure and low temperature. That's high pressure and low temperature. Tell students that the industrial process devised by Carl Bosch actually uses both high temperature and pressure plus an iron-based catalyst. Why doesn't Bosch's process use the conditions predicted by Le Chatelier's principle? A higher than ideal temperature plus a catalyst is needed to increase the reaction rate. Point out that the efficient industrial process must often strike a balance between multiple goals, in this case, yield and reaction time. For every 2 molecules of ammonia made, 4 molecules of reactants are used up, 3 molecules of oxygen and 1 molecule of nitrogen. Therefore, the equilibrium position shifts to make more ammonia. There are then fewer molecules in the system. The pressure decreases, although it will not decrease all the way in the original pressure. As you can see in figure 18.13, increasing the pressure on the system results in a shift in the equilibrium position that favors the formation of product. So you can see that the increased pressure will shift to the right and a reduced pressure will shift to the left. And you have 4 total moles of gas on the left and 2 total moles of gas on the right. The equilibrium position for this reaction can be made to favor the reactants instead of the product. Imagine pulling the plunger of the piston device back up so the volume containing the gases increases. This increase in volume decreases the pressure on the system. To restore the higher starting pressure, the system can produce more gas molecules by the decomposition of some ammonia molecules. Decomposition of 2 molecules of gaseous ammonia produces 4 molecules of reactants, 3 hydrogen and 1 nitrogen. Pressure at the new equilibrium is higher than when the pressure was first decreased, but not as high as it was at the starting equilibrium. Lowering the pressure on the system thus results in a shift of the equilibrium to favor the reactants. Equilibrium constants. Chemists express the position of equilibrium in terms of numerical values. These values relate the amount of reactants to products at equilibrium. In a general reaction, A mole of reactant A and B mole of reactant B react to give C mole of product C and D mole of product D at equilibrium. So you can see that capital A, B, C, and D, those are the actual substances, and lowercase a, b, c, and d are the coefficients. The equilibrium constant, Keq, is the ratio of product concentrations to the reactant concentrations at equilibrium, with each concentration raised to power equal to the number of moles of that substance in the balanced chemical equation. The expression for equilibrium constant can be written this way. Keq equals the molar concentration of C raised to C moles times the molar concentration of D related to D moles, and all of that divided by the product of the molar concentration of A raised to A moles times the molar concentration of B raised to B moles. The exponents in the equilibrium constant expression are the coefficients in the balanced chemical equation. The square brackets indicate the concentrations of substances in mole per liter. The value of Keq depends on the temperature of the reaction. If the temperature changes, the value of Keq also changes. The size of the equilibrium constant shows whether products or reactants are favored at equilibrium. Equilibrium constant. Discuss. Show students how to set up and solve problems involving equilibrium constants. Stress the need to clearly establish what is given and what is being asked. Break down the process into easily followed steps. Point out that the only quantities that can go into the brackets used in equilibrium constant expression are concentrations, or quantities like partial pressures, which are related to concentrations. Warn students not to forget to subtract the number of moles that react from the number of moles originally present in order to determine the number remaining at equilibrium. Point out that it is this value for the concentration of a reactant that is substituted in the denominator of the equation for Keq. Point out that whenever a chemical system reaches equilibrium, the reactants and products have a fixed numerical relationship. This relationship is stated in the equilibrium constant expression. The value of the equilibrium constant can be used to predict the position of equilibrium, because the equilibrium constant refers to an expression in which products are divided by reactants. A Keq value greater than 1 favors the products. Conversely, a Keq value less than 1 favors the reactants. Dinitrogen tetroxide is a colorless gas. Nitrogen dioxide is a brown gas. The flask on the left is in a dish of hot water. The flask on the right is in ice. Interpreting illustrations. How does an increase in temperature affect the equilibrium of a mixture of these gases? An increase in temperature causes the equilibrium to shift towards the formation of more nitrogen dioxide. A value of Keq greater than 1 means that products are favored over reactants. A value of Keq less than 1 means that reactants are favored over products. Keq greater than 1, products favored at equilibrium. Keq less than 1, reactants favored at equilibrium. When the numerical value of an equilibrium constant is calculated, the cancellation of units may or may not lead to a unit for the constant. Chemists have agreed to report all equilibrium constants without stated units. Sample problem 18.1 shows how to calculate the equilibrium constant for the reaction illustrated in figure 18.14. You're going to want to study sample problem 18.1. It will help with your further studies. You can also calculate the equilibrium constant of the reactants and products if you know the equilibrium constant and if you have some information about the initial or final concentration of one of the constituents. For example, bromine chloride decomposes to form bromine and chlorine according to this equation. 2 moles of bromine chloride gas yields 1 mole of bromine gas plus 1 mole of chlorine gas. At a certain temperature, the equilibrium constant for this reaction is 11.1. Suppose that pure bromine chloride is placed in a 1 liter container and allowed to come to equilibrium. Analysis then shows that the reaction mixture contains 4 moles of chlorine. So here we have A moles of the capital A substance yields C moles of C substance and D moles of D substance, all in equilibrium. And so you have 2 moles of bromine chloride yields bromine gas and chlorine gas, 1 mole each. And so what you want to do is you want to say, right, the coefficients of bromine chloride is 2, and that goes up with A above, and then 1 bromine and 1 chlorine. How many moles of bromine and bromine chloride are also present in the equilibrium mixture? According to the equation, when bromine chloride decomposes, equal numbers of moles of bromine and chlorine are formed. At equilibrium, 4 moles of chlorine is present. So 4 moles of bromine must also be present. Because the volume of the container is 1 liter, the concentrations of bromine and chlorine are each 4 moles per liter. These concentrations can be used in the equilibrium constant expression to calculate the concentrations of bromine chloride. So here's the expression. Notice the exponents of 1. That refers to the coefficients of 1. That's the number of moles of bromine and chlorine. So the coefficients, or the number of moles, is actually the exponent. And as it says above, that's going to equal 11.1. Now what we want to do is we want to solve for the concentration of bromine chloride. So now I got rid of the exponents 1 because they're understood, and I simply wanted to show you that they are in actuality there. Rearrange the equation to solve for bromine chloride squared and substitute the known values. So let's just do this slowly. So there's the equilibrium expression, and what we're going to do is we're going to slowly solve for the concentration of bromine chloride. So now you want to take the square root of both sides and put in your concentration of the bromine and chlorine. You can see that it's 4 moles per liter each. Now take the square root. So the square root of 16 divided by 11.1, and that will equal 1.2 moles per liter. That is the concentration. That is what we call molarity. Chlorine and bromine are 2 of the halogens, comparing and contrasting. How are they similar? In what ways are they different? Both are in group 7A, form ions with a -1 charge, and exist as diatomic molecules. Chlorine is a yellow gas, bromine is a brown liquid at ordinary temperatures. It's approximately a gas liquid. Its boiling point is near room temperature. The concentration of the reactant, bromine chloride, is less than the concentrations of the products. So the products, bromine and chlorine, are slightly favored at equilibrium. This is to be expected because Keq is greater than 1. Yellow chlorine gas and brown liquid bromine with its vapor are shown in figure 1815. Section 3, solubility equilibrium. Describe the relationship between the solubility product constant and the solubility of a compound. Predict whether precipitation will occur when two salt solutions are mixed. This is section 3, solubility equilibrium. Here are the key concepts. What is the relationship between the solubility product constant and the solubility of a compound? And how can you predict whether precipitation will occur when two salt solutions are mixed? Solubility product constant, common ion effect are all the vocabulary for section 3. Connecting to your world. X-rays allow physicians to make observations of bones and internal organs without invasive surgery. Sometimes chemical substances are used to improve the clarity of the X-ray image. Barium sulfate is ingested by a patient before X-ray images of the digestive tract are taken. Barium sulfate absorbs the X-rays, thereby producing light areas on the developed X-ray film. However, barium salts are usually toxic, and in this section, you will learn why patients can ingest this poisonous substance without harm. Connecting to your world. All right, let's look at the stomach and how you can examine the stomach using barium sulfate. Why is barium sulfate ingested by a patient before having an X-ray taken of the stomach? Soft tissues don't show up well in X-rays, and the barium sulfate will absorb it, so there's the difference. Why is the digestive system well suited to this type of image enhancement? Chemicals are easily brought into the system and easily removed. Here is table 18.1, solubilities of ionic compounds in water. First, I'm going to uncover the compounds, then the solubility, then the exceptions. So study it carefully and see if you can draw some conclusions. I'll simply let this run for a minute. We may do a lab on this called ChemLogic, so these rules will play an important role in understanding that lab. And we're finished. So carbonates, phosphates, and sulfites are insoluble. Compounds of the alkali metals of ammonium ions are the exceptions. Solubility product constant. Ionic compounds differ in their solubilities. Most salts of the alkali metals are soluble in water. More than 35 grams of sodium chloride will dissolve in only 100 grams of water. Many classes of ionic compounds, however, are insoluble. For example, compounds that contain phosphate, sulfide, sulfite, or carbonate ions are often insoluble. Exceptions are compounds in which these ions are combined with ammonium ions or alkali metal ions. Table 18.1 summarizes the solubilities of many ionic compounds in water. Most insoluble salts will actually dissolve in some extent in water. These salts are said to be slightly or sparingly soluble in water. Discuss. Explain that solubility product constant is closely related to the equilibrium constant that students learned about in section 18.2. Point out similarities in the equations for these two quantities. Write the example problems on the board and carry out the solutions for the solubility product KSP. Focus on how to set up the algebraic expression. Silver chloride is slightly soluble in water. Predicting would adding solid silver chloride to the test tube disturb the equilibrium? No, because the concentration of silver chloride is constant. For example, figure 18.16 shows what happens when the insoluble salt silver chloride is mixed with water. A very small amount of silver chloride is actually dissolved in water. 1 mole of silver chloride yields 1 mole of silver ions plus 1 mole of chloride ions. You can write an equilibrium expression for this process. As long as some undissolved silver chloride solid is present, the concentration of silver chloride is a constant. Thus, the concentration of silver chloride is constant, can be combined with the equilibrium constant to form a new constant. So the product KEQ times the silver chloride concentration equals the product of the silver ions and chloride ions, and that will all equal the KSP, or the solubility product constant. Scale, formed by the precipitation of slightly soluble salts, often builds up around kitchen and bathroom faucets. Applying concepts. Why are insoluble substances hard to remove? Because they don't dissolve in a solvent, such as water. This new constant, the solubility product constant, or KSP, equals the product of the concentrations of the ions, each raised to a power equal to the coefficient of the ion in the dissociation equation. The coefficients for the dissociation of silver chloride are each 1. The value of KSP for silver chloride at 25 degrees Celsius is 1.8 times 10 to the negative 10th. KSP equals silver ions times chloride ions, and the KSP is 1.8 times 10 to the negative 10th. What does the size of the solubility product constant tell you about the solubility of the compound? The smaller the numerical value of the solubility product constant, the lower the solubility of the compound. Here is table 18.2, solubility product constants, KSP, at 25 degrees Celsius. Here we have halides, sulfates, hydroxides, and sulfides, and we also have chromates and carbonates. These are KSPs for certain salts. The solubility product constants for some common sparingly soluble salts are given in table 18.2 on the next page. That's the prior page. The mineral deposits, such as sink drains, such as the one shown in figure 1817, are composed of compounds such as calcium carbonate. The low solubility of such compounds makes them difficult to remove. What does the solubility product constant expression consist of? The product of the concentrations of the ions, each raised to the power equal to the coefficient of the ion in the dissociation equation. Point out that the common ion effect is not a new concept, but an example of Le Chatelier's principle at work. Explain that adding an ion to an equilibrium system containing that ion will cause the equilibrium to shift in the direction that uses up the ion, the common ion effect. In a saturated solution of lead-2 chromate, an equilibrium is established between the solid lead-2 chromate and its ions in solution. What do you think would happen if you added some lead nitrate to this solution? The concentration of lead ion would increase. Immediately, the product of the lead +2 ion and chromate -2 ion would be greater than KSP. Applying Le Chatelier's principle, the stress of the addition of the lead +2 ion can be relieved if the reaction shifts to the left. Lead-2 chromate is slightly soluble in water. A saturated solution of lead-2 chromate is pale yellow. When a few drops of lead-2 nitrate are added to the solution, it becomes cloudy as more lead-2 chromate precipitates. Applying concepts. Explain what happened in B by considering the addition of lead-2 nitrate as a stress on the lead-2 chromate equilibrium. An increase in lead-2 shifts the equilibrium to the left, creating more lead-2 chromate solid. Have students hypothesize how the common ion effect could be used to identify ions in solution. Suggest that they use Table 18.1 to find a common property of salts listed in Table 18.2 in solubility. Explain that saturated solutions of many of the salts in Table 18.2 can be used to test for the presence of different ions in solution. If a precipitate forms when a few drops of an unknown solution is added to a known saturated solution, the unknown solution must have an ion in common with the known solution. Figure 18.18 demonstrates that lead ions combine with chromate ions in solution to form additional solid lead-2 chromate. Lead-2 chromate continues to precipitate from the solution until the product of lead-2 and chromate once again equals 1.8 times 10 to the negative 14. In this example, the lead ion is called a common ion. A common ion is an ion that is found in both salts in a solution. So study the above two equations carefully. Here is Table 18.2 for your review, and it contains the KSP for some fairly insoluble salts. Again, the lower the exponent, the less soluble the salt is. Adding lead nitrate or lead-2 nitrate to a saturated solution of lead-2 chromate causes the solubility of lead-2 chromate to decrease. The lowering of the solubility of an ionic compound as a result of the addition of a common ion is called the common ion effect. Adding sodium chromate to the solution of lead-2 chromate would also produce the common ion effect. The additional chromate ion, a different common ion, would similarly cause the solubility equilibrium to shift to the left and produce more lead-2 chromate. Recall from Connecting to Your World that patients must ingest toxic barium sulfate when having an X-ray taken. Table 18.2 shows that the KSP of barium sulfate is 1.1 times 10 to the negative 10. Considering this low value, it is understandable that barium cannot harm the patient because so little of it is in solution and able to enter the bloodstream. The solubility can be further reduced by adding sodium sulfate, a non-toxic soluble compound that provides the common ion sulfate. What is the common ion effect? The lowering of the solubility of an ionic compound as a result of the addition of one of the ions in the compound, or a common ion. The solubility product, KSP, can be used to predict whether a precipitate will form when solutions are mixed. If the product of the concentrations of two ions in the mixture is greater than the KSP of the compound formed from the ions, a precipitate will form. After precipitation, the solution will be saturated with the precipitated compound. If the product of the concentrations is less than the KSP, no precipitate will form and the solution is unsaturated. Suppose you have a 0.5 liter of 0.002 molar barium 2 nitrate and mix it with 0.5 liters of 0.008 molar sodium sulfate. You then have 1 liter of solution. The insoluble compound that could precipitate is barium sulfate. To predict whether a precipitate of barium sulfate will form, you need to determine the concentration of the ion after the dilution that occurs on mixing. Precipitation will occur if the product of the concentrations of the two ions of barium and sulfate exceeds the KSP of barium sulfate, which is 1.1 times 10 to the negative 10. Because each solution was diluted with an equal volume of the other solution, the concentrations of both barium and sulfate after mixing will be half of their original concentrations. Thus, in combined solution, barium ion equals 0.001 molar and sulfate ion equals 0.004 molar. A precipitate of barium sulfate forms as barium nitrate and sodium sulfate solutions are mixed. Applying concepts. What is the product of the concentrations of barium ion and sulfate ion after precipitation is complete? KSP is 1.1 times 10 to the negative 10, and there are no units. These concentrations can now be multiplied together as a trial product and the result compared with the KSP. The KSP of barium sulfate is 1.1 times 10 to the negative 10, so the trial product is larger than the KSP. A precipitate will form. Barium sulfate will precipitate until the product of the concentrations of the ions remaining in solution equals 1.1 times 10 to the negative 10. Figure 1819 shows the mixing of the solution and the precipitation of barium sulfate. Other compounds in radiology. Barium sulfate is just one of many compounds used as contrast materials in radiology. Barium compounds are used to look at gastrointestinal areas. Water-soluble ionated compounds are contrast materials injected to make blood vessels, urinary tract, and spinal canals visible to X-rays. Naturally placed or injected air also functions as a contrast material. All right, let's look at section 4, entropy and free energy. Identify two characteristics of spontaneous reactions. Describe the role of entropy in chemical reactions. Identify two factors that determine the spontaneity of reaction, and define Gibbs free energy change. Now let's look at the key concepts for the section. What are two characteristics of spontaneous reactions? What part does entropy play in chemical reactions? What two factors determine the spontaneity of a reaction, and is the Gibbs free energy change positive or negative in a spontaneous process? Vocabulary: free energy, spontaneous reaction, non-spontaneous reaction, entropy, law of disorder, Gibbs free energy change. Connecting to your world. Fire in homes, barns, and other places sometimes seem to start on their own without any application of heat for an external source. These fires could be caused by spontaneous combustion inside a pile of oily rags or a stack of hay that is not thoroughly dried. Decomposition causes heat to build up. If the existing conditions do not allow the heat to escape, the temperature can build up enough to cause a fire. In this section, you will learn about the conditions that will produce a spontaneous chemical reaction. Connecting to your world, discuss and relate. Spontaneous chemical reaction. What conditions produce a spontaneous chemical reaction? Students may suggest reactions that have a low activation energy, reactions that involve active elements such as an alkali metal, combustion reactions above the kindling temperature, or reactions in solution that produce a precipitate. Continue with free energy and spontaneous reactions. Discuss what is meant by work. Point out that work is done on a gas when a force is applied to reduce its volume. Work is done by rapidly expanding gases, such as those produced in an explosion. Is work done on molecules when the temperature is raised or when chemical bonds are broken? Yes, in both cases. How is energy related to work? Work and energy have the same units. Relate. Commercially, chemical reactions are usually carried out to manufacture a chemical substance or to produce energy. The commercial value of a chemical reaction depends on the conditions under which it occurs spontaneously and on the reaction rate. Emphasize that all spontaneous reactions release free energy. Students may think that non-spontaneous reactions is one in which no products are formed. Remind them that in a reversible reaction, under a given set of conditions, one reaction is always spontaneous and the other reaction is non-spontaneous. Therefore, the difference between spontaneous and non-spontaneous reactions is the amount of products at equilibrium. Look back at some of the equations in the last section to see if you can find information that supports that. Free energy and spontaneous reactions. Many chemical and physical processes release energy that can be used to bring about other changes. For example, some of the energy liberated in a chemical reaction can be harnessed to do work, such as driving the pistons of an internal combustion engine. Free energy is energy that is available to do work. Just because free energy is available to do work, however, does not mean it can be used efficiently. The internal combustion engine in a car is only about 30% efficient. Not really that high, actually. That is, only about 30% of the free energy released by burning gasoline is used to propel the car. The remaining 70% is lost as friction and waste heat. However, no process can be made 100% efficient. You can get close depending upon certain engines, but certainly not the internal combustion engine. Even in living things, which are among the most efficient users of free energy, processes are seldom more than 70%. Another complication, in addition to energy efficiency, is that energy can be obtained from a reaction only if the reaction actually, rather than theoretically, occurs. In other words, although a balanced equation can be written for a chemical reaction, the reaction may not actually take place. For example, you can write an equation for the decomposition of carbon dioxide to carbon and oxygen. This equation, which represents the reverse of combustion, is balanced. However, experience tells you that the reaction represented by the equation does not tend to occur. Carbon and oxygen react to form carbon dioxide, not the reverse. So the world of balanced chemical equations is really divided into two groups. One group contains equations representing reactions that actually occur. The other group contains equations representing reactions that do not tend to occur, or at least not efficiently. Explain that a fireworks display is a result of highly spontaneous reactions that release a large quantity of free energy. Also explain that this reaction requires a very high initiation temperature to produce the fast reaction rate observed. Fireworks displays are the result of highly favored spontaneous reactions. A large quantity of free energy is released. The first and more important group involves processes that are spontaneous. A spontaneous reaction occurs naturally and favors the formation of products at the specified conditions. Spontaneous reactions produce substantial amounts of products at equilibrium and release free energy. The colorful fireworks display shown in figure 18.20 is an example of a spontaneous reaction. In contrast, a non-spontaneous reaction is a reaction that does not favor the formation of products at the specified conditions. Non-spontaneous reactions do not give substantial amounts of products at equilibrium. Consider again the reversible decomposition of carbonic acid in water. Carbonic acid, 1 mole aqueous, yields 1 mole of carbon dioxide gas and 1 mole of water, where you have 99% of the product represents the right side of the equation. Carbonic acid is the reactant in the forward reaction. If you could start with pure carbonic acid in water and let the system come to equilibrium, more than 99% of the reactants would be converted to the products carbon dioxide and water. These products are highly favored at equilibrium. The natural tendency is for carbonic acid to decompose to carbon dioxide and water. Thus, the forward reaction is spontaneous and releases free energy. In the reverse reaction, carbon dioxide and water are the reactants, and carbonic acid is the product. A precipitate of cadmium sulfate forms spontaneously when solutions of sodium sulfide and cadmium nitrate are mixed. Is free energy released in this reaction? Free energy is released because the reaction is spontaneous. If you permit a solution of carbon dioxide in water to come to equilibrium, less than 1% of the reactants combines to form carbonic acid. The reactants show little natural tendency to go to products. Thus, the combination of carbon dioxide and water to form carbonic acid is non-spontaneous. In nearly all reversible reactions, one reaction is favored over the other. Another example shown in figure 18.21 is the spontaneous reaction of aqueous cadmium nitrate with aqueous sodium sulfide to produce aqueous sodium nitrate and solid yellow cadmium sulfide. Cadmium sulfide is highly favored in this equilibrium. The reverse reaction, the production of cadmium nitrate and sodium sulfide from cadmium sulfide and sodium nitrate, is non-spontaneous according to the below equation. Have students consider the combustion of glucose to produce carbon dioxide and water. Point out that the reverse of this reaction is the overall reaction for photosynthesis, the process by which plants make glucose using carbon dioxide and water. Ask students to consider the magnitude of the free energy value for the photosynthesis reaction, plus 2868 kilojoules per mole. They should realize that the reaction is non-spontaneous under ordinary conditions. It is important to note that the terms spontaneous and non-spontaneous do not refer to how fast reactants go to products. Some spontaneous reactions go so slowly that they appear to be non-spontaneous. The reaction of sugar and oxygen, for example, produces carbon dioxide and water. However, a bowl of sugar on a table does nothing, and you might assume that the equilibrium among sugar, oxygen, carbon dioxide, and water greatly favors the sugar and oxygen. The equilibrium does favor the products, but at room temperature the reaction is so slow that it takes thousands of years to reach equilibrium. Many spontaneous reactions are required for a plant to grow. Non-spontaneous reactions can occur when they are coupled with spontaneous reactions. Inferring. What is another requirement for this photosynthesis reaction? Light energy. When you supply energy in the form of heat, however, the reaction is fast. Then it is obvious that the formation of carbon dioxide and water is highly favored. Some reactions that are non-spontaneous at one set of conditions may be spontaneous at other conditions. Changing the temperature or pressure, for example, may determine whether or not a reaction is spontaneous. The non-spontaneous photosynthesis reaction summarized in figure 18.22 could not be driven to completion without the energy supplied by sunlight. Sometimes a non-spontaneous reaction can be made to occur if it is coupled to a spontaneous reaction, a reaction that releases free energy. Coupled reactions are a common feature of the complex biological processes that take place in living organisms. Within cells, a series of spontaneous reactions release the energy stored in glucose. As you will learn in Chapter 24, molecules in cells can capture and transfer free energy to non-spontaneous reactions, such as the formation of proteins. If a reaction releases free energy, is the reaction spontaneous or non-spontaneous? Spontaneous. Absolutely. Entropy. Recall that heat, enthalpy, changes accompanying most chemical and physical processes. The combustion of carbon, for example, is exothermic and spontaneous. The heat released during this reaction is 393.5 kilojoules for each mole of carbon graphite burned. You might expect that only exothermic reactions would be spontaneous. Some processes, however, may be spontaneous even though they absorb heat. For example, consider physical process of melting ice to water. How could that possibly occur? It is not exothermic. As it turns from solid to a liquid, 1 mole of ice, 25 degrees Celsius, absorbs 6.0 kilojoules of heat from its surroundings. Ice melts spontaneously at 25 degrees Celsius even though the water produced contains more heat than the ice from which it forms. Considering only enthalpy changes, the energy of the water seems higher than the energy of the ice. That would seem to violate the rule that in spontaneous processes, the direction of the change in energy is from higher energy to lower energy. That is, free energy is released. Yet, this process occurs anyway. Some factor other than the enthalpy change must help determine whether a physical or chemical process is spontaneous. The other factor is related to order. You are familiar, probably, with everyday ideas about order and disorder. For example, a handful of marbles is relatively ordered in the sense that all the marbles are collected in one place. It is improbable that when permitted to fall, the marbles will end up in the same neat arrangement. Instead, the marbles scatter on the floor. They become disordered. Scattered marbles have a higher entropy than a handful of marbles. Entropy is a measure of the disorder of a system. Origin of entropy. The term entropy was coined by the German physicist Rudolf Clausius in 1865. He used the term to describe the portion of free energy that is unavoidably lost to the environment as waste heat. Clausius pointed out that in any process involving the flow of energy, there is always some loss, so that the entropy of the universe is continually increasing. Clausius. The entropy of a recently cleaned and orderly room is low. However, over time, a room tends to become disorderly. Entropy has a tendency to increase. Applying concepts. Which has the greater entropy? An assembled jigsaw puzzle or the pieces in the box? The pieces in the box. The concept that physical and chemical systems attain the lowest possible energy has a companion idea called the law of disorder, which states that the natural tendency is for systems to move in the direction of maximum disorder or randomness. You already know something about this natural tendency towards disorder. Maybe the photographs in figure 1823 look familiar to you. More than likely, your bedroom is neat and clean at the beginning of the week, but unless you put energy work into maintaining it, your room becomes messy by the end of the week. The law of disorder, entropy change, also operates at the level of atoms and molecules, and so it is a factor in determining the direction of chemical reactions. Entropy is a measure of disorder of a system. A. For a given substance, the entropy of the gas is greater than the entropy of a liquid or the solid. Similarly, the entropy of the liquid is greater than that of the solid. Thus, entropy increases in reactions in which solid reactants form liquid or gaseous products. Entropy also increases when liquid reactants form gaseous products. Entropy is a measure of disorder of a system. B. Entropy increases when a substance is divided into parts. For instance, entropy increases when a crystalline ionic compound such as sodium chloride dissolves in water. This is because the solute particles, sodium ions and chloride ions, are more separated in solution than they are in the crystalline form. Entropy is a measure of disorder of a system. C. Entropy tends to increase when temperature increases. As the temperature increases, the molecules move faster and faster, which increases the disorder. Explain that in a game of chance, the probable event can happen in many ways. The same is true of order and disorder. An ordered arrangement conforms to some chosen requirements. All other arrangements are called disordered. Because far more arrangements are possible in the latter category, disorder is the natural condition of things. Review the different situations that increase entropy. Ask students for everyday examples in which entropy increases or decreases. For example, fans entering a stadium and fans seated during a game. An increase in entropy favors the spontaneous chemical reaction. A decrease favors the non-spontaneous reaction. Figure 18.24 on the following page illustrates some generalities that will help you to predict the course of many reactions. That we've already seen. That was about 3 or 4 slides ago. Enthalpy, entropy, and free energy. In every chemical reaction, heat is either released or absorbed, and entropy or randomness either increases or decreases. How do these two energy factors determine the course of a reaction? The size and direction of enthalpy changes and entropy changes together determine whether a reaction is spontaneous. That is, whether it favors products and releases free energy. An exothermic reaction accompanied by an increase in entropy is definitely spontaneous because both factors are favorable. The combustion of carbon, for example, is exothermic. Entropy also increases as solid carbon is converted to gaseous carbon dioxide. Evidence suggests that Earth is being warmed because of the greenhouse effect, which is largely due to the release into the atmosphere of carbon dioxide produced by combustion. Another aspect of the greenhouse effect that relates to the topic is spontaneity, is the increase in the quantity of atmospheric carbon dioxide gas that would occur if the oceans became warmer. Carbon dioxide is quite soluble in water. The oceans currently contain a great deal of dissolved carbon dioxide. If the oceans become warmer, more carbon dioxide could be released into the atmosphere because CO2, like other gases, is less soluble in warm ocean water than in cool ocean water. The process whereby carbon dioxide dissolves in ocean water would become non-spontaneous, and the reverse process, the release of carbon dioxide gas, would become spontaneous. The increased temperature would release more carbon dioxide, which would further increase temperature, and so on. Free energy refers to more than just the enthalpy change, delta H, that occurs in a chemical reaction. Free energy combines delta H with the change in entropy, delta S. Delta H and delta S are usually assumed to be constant for the same reactions at different temperatures. Therefore, the contribution to the free energy from the T delta S term comes mostly from the temperature itself. Gibbs free energy, discuss and relate. Have students compare Table 18.3 and Figure 18.25. These visuals contain the information that students need to explain why some reactions are spontaneous and others are not. What changes can occur during a reaction to favor spontaneity. Changes in which heat is released and entropy increases, such as burning wood, very spontaneous. Under what conditions is a reaction least likely to be spontaneous? When heat is absorbed and entropy decreases. Not going to happen. What happens when one change favors spontaneity and one change does not? The relative strength of the opposing changes determine the outcome. For reactions that lead to equilibrium, the magnitudes of the enthalpy and entropy changes determine the point at which the opposing reactions are balanced. Here is Table 18.3, how changes in enthalpy and entropy affect reaction spontaneity. It is an excellent table and summarizes all of the different conditions in one convenient table. Study it carefully and understand every single box that's uncovered. If you don't understand, you have two options. One, go back and read the section, and or two, ask me in class. Very powerful table. Notice when temperature is a factor in determining spontaneity. And there you have it. Because both factors are favorable, the reaction must be spontaneous. The reverse reaction, production of carbon and oxygen from carbon dioxide, is non-spontaneous. Neither the enthalpy nor the entropy changes favorable. A reaction is also spontaneous if a decrease in entropy is offset by a large release of heat. Similarly, an endothermic or heat-absorbing reaction is spontaneous if an entropy increase offsets the heat absorption. For example, enthalpy change and entropy change work in opposition when ice melts. The melting of ice is endothermic, but the process is still spontaneous above 0 degrees Celsius. At such temperatures, the absorption of heat is more than offset by a favorable entropy change. Table 18.3 summarizes how entropy and enthalpy changes affect the spontaneity of chemical reactions. Notice that either of the two variables, but not both, can be unfavorable for a spontaneous process. Non-spontaneous reactions, those in which the products are not favored, can have enthalpy changes, entropy changes, or both working against them. For example, a reaction might be highly endothermic with a large decrease in entropy. In that case, both changes work against the formation of products and the reaction is non-spontaneous. In another case, a reaction may be exothermic but involves a decrease in entropy large enough to offset the favorable enthalpy change. The combination of the enthalpy change and the change in entropy for a reaction determines whether or not the reaction is spontaneously. This 18.25 figure summarizes everything brilliantly. This reaction will also be non-spontaneous. Alternatively, an endothermic reaction could have an increase in entropy too small to overcome the unfavorable enthalpy change. Figure 18.25 on the following page summarizes the relationship among enthalpy, entropy, and free energy changes for spontaneous reactions. What two energy factors determine the course of a reaction? Enthalpy and entropy. Gibbs free energy. Recall that in every spontaneous process, some energy becomes available to do work. This energy, called the Gibbs free energy change, is the maximum amount of energy that can be coupled to another process to do useful work. The change in Gibbs free energy is related to the change in entropy, S. and the change in enthalpy, H, of the system by the free energy equation, which is delta G, the change in free energy, equals delta H, the change in enthalpy, minus the temperature times the change in entropy, delta S, or T delta S. The temperature T is in kelvins. All spontaneous processes release free energy. The numerical value of delta G is negative in spontaneous processes because the system loses free energy. Non-spontaneous processes require that work be expended to make them go forward at the specified conditions. Therefore, the numerical value of G is positive for a non-spontaneous process. However, a reaction that is non-spontaneous under one set of conditions may be spontaneous under another set of conditions. To see the effect of temperature on the spontaneity of a reaction, consider this chemical reaction. Solid calcium carbonate decomposes to give calcium oxide and carbon dioxide. Calcium carbonate, formula unit, and then you have the formula unit of calcium oxide plus the molecule carbon dioxide. In this reaction, the entropy increases because one of the products formed from the solid reactant is a gas. Figure 18.26. The combination of the enthalpy change and the change in entropy for a reaction determines whether or not the reaction is spontaneous. Study this very carefully, very important figure. However, the reaction is endothermic and the entropy increase is not great enough to offset the unfavorable enthalpy change. Thus, the reaction is non-spontaneous at ordinary temperatures. The effect of an entropy increase, however, is magnified as the temperature increases. At temperatures above 850 degrees Celsius, the favorable entropy temperature term, T delta S, in the equation, delta G equals delta H minus T delta S, outweighs the unfavorable enthalpy change, delta H, or term. Under these conditions, the decomposition of calcium carbonate becomes spontaneous. Calcium oxide obtained from this spontaneous reaction is used to neutralize acid soil, as shown in figure 18.26. Section 5. The progress of chemical reactions. Describe the general relationship between the value of the specific rate constant K and the speed of a chemical reaction. Interpret the hills and valleys in a reaction progress curve. What is the general relationship between the value of the specific rate constant K and the speed of a chemical reaction? What do the hills and valleys in a reaction progress curve represent? Rate law, specific rate constant, first order reaction, elementary reaction, reaction mechanism, intermediate. Let's look at the Tour de France for a minute. There's the Tour de France, that's the Arc de Triomphe. The Tour de France is one of the most famous bicycle races in the world. It is held from mid-July to early August. During the course of the race, cyclists travel almost 4,000 kilometers and cross steep mountains at heights of 1,600 meters or more. To cross these high mountains requires extra amounts of energy. A chemical reaction can be thought of as a process involving peaks and valleys also. In this section, you will learn about the energy requirements for a chemical reaction to progress from initial reactants to final products. Connecting to your world. Tour de France. How is the Tour de France bicycle race like the reaction progress curve for a complex reaction? A series of chemical reactions may require more energy at some points, i.e. activation energy, and release energy at other points. Rate laws. The rate of a reaction depends in part on the concentrations of the reactants. For a reaction in which reactant A forms product B, in one step you can write a simple equation, A yields B. The rate at which A forms B can be expressed as the change in A, delta A, with time, where concentration A1 is the initial step or the initial concentration of A at time t, and concentration A2 is the concentration of A at a later time t2. Rate equals delta A over delta T, or the concentration A2 minus concentration of A1 over T2 minus T1. Because A, the reactant, is decreasing, the concentration A is smaller at a later time than initially, and so A will always be negative. The negative sign in the expression is needed to make the rate positive, as all rates must be. The rate of disappearance of A is proportional to the concentration of A. Negative delta A over delta T is approximately equal to or proportional to the concentration of A. The proportionality becomes an equation with the insertion of a constant K. Rate minus delta A over delta T equals K times the molar concentration of A. This equation, called a rate law, is an expression for the rate of a reaction in terms of the concentration of reactants. The specific rate constant K for a reaction is a proportionality constant relating the concentration of reactants to the rate of the reaction. The magnitude of the specific rate constant depends on the conditions of the reaction and is determined experimentally. The value of the specific rate constant K is large if the products form quickly. The value is small if the products form slowly. The order of a reaction is the power to which the concentration of a reactant must be raised to give the experimentally observed relationship between concentration and rate. So the rate minus A delta A over delta T equals K times the molar concentration of A. The graph shows how the concentration of a reactant changes as a reaction proceeds. This is figure 18.27. So A, navigate. What is the dependent variable? B, read. What happens to the relative concentration of reactant A as time progresses? And C, interpret. The short colored lines illustrate the reaction rates at two distinct points of time. Is the initial rate or the subsequent rate faster? Navigate. What is the dependent variable? What is the dependent variable? Relative concentration of A. Read. What happens to the relative concentration of reactant A as time progresses? It decreases. Quite clearly, it decreases. And the short colored lines illustrate the reaction rates at two distinct points of time. Is the initial rate or the subsequent rate faster? That's C, interpret. Initial rate. Initial rate. Figure 18.27 explain that the slope of a straight line is the ratio of the rise y to the run x. Demonstrate how to calculate the slope of several straight lines. Explain that the slope of the tangent to the curve at any point is the slope of the curve at that point. Discuss how to calculate the rate of reaction by determining the slope of the tangent line for the 2 points shown on the graph. Have students calculate the initial rate of reaction. Next, have students calculate the rate at time equals 2.5. So you see the rate equals 5 given the data. And now let's do 2.5. And that rate is going to be quite clearly 1.5. Point out that the rate decreases as expected as the concentration of reactant A decreases. Discuss how the effect of concentration on the reaction rate is expressed as a quantitative relationship. Each rate expression contains a rate constant K, which is specific to the reaction. A knowledge of this dependence not only allows prediction of the actual rate, but also gives clues to the step-by-step mechanism by which the reaction occurs. Demonstrate how to set up the rate equation for a chemical reaction, such as the formation of water from hydrogen and oxygen. The order of a reaction is the power to which the concentration of a reactant must be raised to give the experimentally observed relationship between concentration and rate. In a first-order reaction, the reaction rate is directly proportional to the concentration of only one reactant. The conversion of A to B in a one-step reaction is an example of a first-order reaction. The reaction rate is proportional to the concentration of A raised to the first power. As a first-order reaction progresses, the rate of reaction decreases as shown in figure 18.27. The decrease occurs because the concentration of reactant is decreasing. On a graph, the rate A over delta t at any point equals the slope of the tangent to the curve at that point. For a first-order reaction, a reduction of molar concentration of A by 1/2 reduces the reaction rate by 1/2. In some kinds of reactions, such as double replacement, two substances react to give products. The coefficients in the general equation for such a reaction are represented by lowercase letters. For a one-step reaction of A with B, the rate of reaction is dependent on the concentration of both A and B. When each of the components A and B in the rate law equals 1, the reaction is said to be first order in A, first order in B, and second order overall. The overall order of a reaction is the sum of the exponents for the individual reactants. For any one-step reaction, the experimentally determined exponents in the rate law are the same as the coefficients A and B in the chemical equation. However, the exponents in the rate law and the coefficients in the equation do not correspond in most real reactions because most reactions are more complex than the one-step reaction used in the examples. The actual order of the reaction must be determined by experiment. How can you determine the rate of a reaction from a graph of reactant concentration versus time? Calculate the slope of the tangent to the curve at any point. Reaction mechanisms. If enough information were available, you could graph all the energy changes that occur as reactants are converted to products in a chemical reaction. Such a graph would constitute a reaction progress curve. The simplest reaction progress curve is for an elementary reactions, such as the one shown in Figure 18.5. An elementary reaction is a reaction in which reactants are converted to products in a single step. Such a reaction has only one activation energy peak between reactants and products, and thus only one activated complex. Most chemical reactions consists of a number of elementary reactions. A reaction progress curve shows an activation energy peak for each elementary reaction. Valleys indicate the formation of intermediates. Figure 28. The energy of reaction, y-axis, determined experimentally, is plotted versus time, or reaction progress, x-axis. The graph shows that the slope changes from positive to negative frequently during the course of the reaction. The usual way to construct such a graph is to measure the energy of several points, most likely at the tops of the energy barriers and at the positions of the intermediate. The remaining points can be interpolated. Displaying the data in each graph provides a more complete picture than a table of data. Figure 28, let's ask some questions. How many elementary reactions are part of this reaction? 4. How many intermediates are formed? 3. Study the graph carefully, it's not very difficult. How would a catalyst affect the energy of the reactants and the energy of the products of this reaction? It would have no effect. The series of elementary reactions or steps that take place during the course of a complex reaction is called a reaction mechanism. The reaction progress curve for a complex reaction resembles a series of peaks and valleys. As you can see in Figure 18.28, the peaks correspond to the energies of the activated complexes. Each valley corresponds to the energy of the intermediate. An intermediate is a product of one of the steps in the reaction mechanism. It becomes a reactant in the next step. Intermediates have a significant lifetime compared with an activated complex. They have real ionic or molecular structures and some stability. Ozone is an essential gas in the stratosphere. It absorbs UV radiation from the sun, keeping the UV levels at Earth's surface below a lethal level. The Chatman Cycle describes the equilibrium of O2 and O3 in the stratosphere. In the first step, O2, solar radiation, goes to 2 atoms of oxygen. Next, an atom of oxygen combines with O2 to form O3. Natural levels of nitrogen oxides react with O and O3 to keep O3 at an equilibrium of 6 parts per million. Human-generated chemicals such as chlorinated fluorocarbons change the equilibrium so that less ozone is produced. UV radiation levels at Earth's surface go up as a result. They are reactive enough, however, to take part in the next step of the reaction mechanism. Intermediates do not appear in the overall chemical equation for a reaction. The reaction mechanism for the decomposition of nitrous oxide, N2O, for example, is believed to occur in 2 elementary steps. Notice that in the first elementary step, oxygen atoms are formed. These are an intermediate product in this step of the mechanism. Study those three equations carefully. They are a reactant in the second step, and they disappear when the two elementary reactions are summed to give the final chemical equation. This illustrates an important general point. The overall chemical equation for a complex reaction gives no information about the reaction mechanism. Reaction mechanisms must be determined experimentally. I have also included the three equations below for your further consideration.